So that's the main idea. And so right now I would like to, so that's the main idea about DB84, the decoy state variant protocol. So they would also share the intensities. Here I would like to go a bit different topic to speak about, to say a few words about this quantum, the satellites that are used in quantum communication. So in fact, currently we do not have many satellites in orbits that do perform quantum communications protocols. One of those that will be launched is called Nanobob satellite. As just for example, I want to show how it looks like. So Nanobob satellite will launch 2025, but here you can see that it has its 12U size and it has this very big light collection optics. It's of 150 millimeters in diameter, and yeah. So just to give you sense how this kind of satellite would look like. Well, he also has this laser beacon and also polarization analysis and detection module, of course. So let's go a bit deeper into this polarization analysis and detection module and see how it actually detects and analyzes the particles for BB84 protocol. All right. So especially the design of the Nanobob satellite. Polarization analysis and detection module, I think would be more or less similar for many future missions of quantum communications. Well, because it's governed by this fundamental physics. So that's the reason I chose to speak exactly about Nanobob satellite, because the information about it was really available on the internet. It's built by the French and Swiss, I think, scientists from universities. So they publish all the information about the mission itself. So at the input of the satellite, we have this. We have this Schmidt-Cassegrain telescope that's actually can accept different light waves. So that would, for example, for classical channel, it would use 880 nanometers, and for the quantum channel, it would use 880 nanometers, and for the classical channel, it would use 530 nanometers. So afterwards, you would have some kind of dichroic beam splitter that would split the wavelength accordingly. So it would split either the classical or the quantum. So the classical wave would go here. The classical wavelength would go to this part, and the quantum would go to this part. So in this classical part, we would have some kind of another beam splitter that would actually redirect some part of the photons to the quadrant detector that just would use for the alignment and purposes of the satellite. And afterwards, we would have also the photodiode that would detect the classical information itself. Regarding the quantum channel, we would have this beam splitter, and afterwards, so after being split here, it would go to another beam splitter, where the particles, those quantum particles, photons would be split, would go to the horizontal vertical basis polarizing beam splitter, and here it would be detected either by the horizontal or vertical photodiode, and that's how it would be able to actually know that where we actually detected the particles. And afterwards, it would be also split to according to diagonal or anti-diagonal basis. So yeah, so that's the main idea about this light collection optics and how we actually would perform measurements for the satellites. That's actually the system that's used for the Nanobob satellite.